You know, when you look at a flight map, it's easy to just see a bunch of lines connecting dots. But what if there's a hidden structure, a hidden logic to it all? Well, there is. Today, we're going to deconstruct the entire domestic airport network of India. We'll use the tools of network science to pull back the curtain and see how this absolutely vital system really works and what it tells us about how a nation connects itself. Let's dive in.
So here's our flight plan. First, we'll talk about how you even model an airport network. Then we'll get into this cool idea called the small world phenomenon. After that, we'll look at the big players, the hubs, and this idea of a scale-free structure. Next, we'll analyze the actual flow of traffic, because that's where things get really interesting. And finally, we'll wrap it all up with the key findings and some solid advice for exam prep.
Okay, so how do you even begin to analyze something as massive and complex as a country's entire airport system? You can't just stare at a map, right? The very first step is to create a model, to basically translate that real-world jumble of airports and flight paths into a clean, data-rich network that we can actually measure and understand.
Now, there are two basic ways to look at this. On one hand, you have the unweighted network. Think of this as the basic blueprint. It just asks a simple question. Is there a direct flight between two airports? It's a simple yes or no. But then you have the weighted network, and this adds a crucial layer of, well, reality. It asks how many flights are on that route. This is the difference between just knowing a road exists and knowing exactly how busy that road is.
The specific network we're breaking down here is the Airport Network of India, or ANI, and we're using data from back in 2004. So, in network speak, we've got 79 nodes, those are the airports, and they're connected by 442 directed links, which are just the one-way flight routes. This dataset was super comprehensive for its time. It included all the major domestic airlines, giving us a really solid snapshot of India's aviation system.
All right, now that we have our model, we can start asking some really cool questions. Like, have you ever booked a flight and been surprised at how easy it is to get from some tiny city to another one clear across the country, maybe with just one layover? That feeling you have, that's actually a real thing that network scientists call the small world phenomenon. So let's see if India's airport network actually has this property.
So what is a small world network? It's kind of a funny mix. On one side, it's super clustered. That means that airports that are connected to your airport are probably also connected to each other. It's like friends in a small town. But on the other side, the average number of steps to get from any single point to any other point is incredibly small. The classic example you've probably heard of is 6 degrees of separation.
So, does India's network fit the bill? Oh, absolutely. The first big clue is the average shortest path length, which comes out to 2.2593. Now, what that means in plain English is that, on average, you can fly between any two airports in the entire country with just a little over one layover. That is amazingly efficient.
And here's the second piece of the puzzle, the clustering coefficient. It's about 0.66. Now that number might not mean much on its own, but it is nearly 10 times higher than what you'd get if you just wired up these airports at random. That tells us there's a ton of local structure. So you've got a really short path length and super high clustering. That right there is the textbook definition of a small world network. And this slide is where those abstract numbers get real. This is what it means for you as a traveler. Check this out. Only about 7% of all possible journeys are direct flights. But just add one stopover, and suddenly you can reach another 61% of all possible destinations. Add a second stop, and you've got almost all of them. All in all, about 99% of every possible trip can be done with 2 changes or less.
Now, all this efficiency points to something really important. Not all airports are created equal. The whole network really leans on a few key players to connect everybody else. And that brings us to the whole idea of hubs and what's called a scale-free structure.
To really get this, we need a tool called the degree distribution. It sounds technical, but it's a really simple idea. Just imagine you wrote the name of all 79 airports on slips of paper and threw them in a hat. The degree distribution just tells you the odds of pulling out an airport that has, say, only 5 connections versus pulling out one with 50.
And this leads us to a really fundamental question about how the network is designed. Is it a democracy, where most airports have about the same number of routes? Or is it a monarchy, where you have a few massive hub airports that completely dominate and connect everyone else?
And this graph gives us the answer, loud and clear. Now, this is a special kind of graph called a log-log plot. Don't worry about the details. All you need to know is that when the data makes a nice, straight, downward-sloping line like this, that is the classic signature of what we call a power law or scale-free network.
And what that means for us is that you have tons and tons of airports with just a few connections, and then a tiny, tiny handful of airports with a massive number of connections. So to answer our question, it's a monarchy. The hubs rule.
So how does a structure like this even happen? Well, it's often explained by this rich get richer idea. Think about it. When an airline wants to add a new route, are they more likely to connect to a massive hub like Delhi or Mumbai or to some small regional airport? The hub, right? Over time, this tendency to connect to the already popular nodes is what creates this extreme hub-dominated structure. But the paper makes a great point here. This power law isn't perfect. If you look at the graph, you can see the line kind of bends off at the very end. And that's where the real world crashes the party. There are physical limits. There's a real cost and a real capacity constraint to how many flights an airport can handle. Even the biggest, baddest hub can't just grow forever.
Okay, so we've got the blueprint of the network down. We know it's a small world and it's dominated by hubs. But now let's add back that layer of reality we talked about earlier, the traffic. Because it's not just about who you're connected to, it's about how much stuff is actually flowing through those connections.
To analyze traffic, we're going to need a new measurement. We used the term degree to just count an airport's connections. Now we're going to use strength to measure its total traffic, the actual number of weekly flights it handles. It's the difference between counting how many roads lead into a city and counting how many cars are actually on those roads.
And this is where it gets really, really insightful. The study found this incredible mathematical relationship between an airport's connections, its degree, and its traffic, its strength. You see, in a perfectly balanced world, if you doubled your connections, you double your traffic. But that's not what happens here. The relationship is what we call superlinear. That exponent, 1.43, means that when a big hub adds new connections, its traffic grows way faster than you'd expect. The big airports don't just have more routes. On average, each one of those routes is much, much busier.
Okay, these next two graphs, they reveal what is probably the most important finding in the whole paper. They're all about who connects to whom. Does a huge hub like Delhi tend to connect to another huge hub like Mumbai? Or does it tend to connect to a whole bunch of smaller airports? The answer to that question reveals the fundamental strategy of the entire network. And what the data shows is something called a disassortative structure. This was a major discovery, so let's break down exactly what that means. So, what on earth is assortativity? It's actually pretty simple. Assortative mixing is when birds of a feather flock together. Big, important nodes tend to connect to other big, important nodes. This happens a lot in social networks. But the Indian airport network is the opposite. It's disassortative. This is the classic hub and spoke model. The big hubs prefer to connect to lots of smaller, less connected airports, basically spreading connectivity all across the country.
And here is the crucial point, the big contrast. The global world airport network, that's largely assortative. Hubs connecting to other hubs. But the national network of India is disassortative. Hubs connect to spokes. This is a huge deal because it suggests there might be a fundamental difference in how national networks develop, maybe because of political or economic reasons, compared to global networks, which are all about linking the biggest economic centers.
All right, we have covered a ton of ground. Let's pull everything together and land this thing. If you are studying this for an exam, this next part is what you really want to lock in.
So, in a nutshell, the airport network of India is 5 key things. 1, it's a small world network, which makes it super efficient to travel on. 2, it's scale-free, so a few major hubs do most of the heavy lifting. 3, it has a hierarchical structure. 4, and this is the big one, it's disassortative, with that hub and spoke model that's different from the global network. And 5, the traffic is massively concentrated on the main routes that connect those big hubs.
So how do you actually use this knowledge on an exam? Just follow this simple 3-step formula. First, you define the concept you're talking about, like disassortativity. Second, you state the specific finding from the paper, and if you can remember the key numbers, even better. And third, you explain what it means in the real world. This structure shows you don't just know the what, you also understand the so what. And that's going to break down the hidden logic that shapes our world, one flight at a time.